Fluorine always makes molecules more inert, including solvents. Or does it? There's an interesting series of solvents referred to as Novex solvents. They're made by a company called 3M. In fact, one of these solvents has even been featured in a Nile Red video.
But I think that all this water might have actually been worse than the fire. Thankfully, though, this wasn't water, and it was instead something called Novex 7100.
These solvents can be used for a number of different purposes, including heat transfer mediums as coolants for servers. These solvents can be used in place of air, and so these solvents can just suck a ton of heat out of the server as it's producing lots of heat. This can be important for data centers, for instance. And I'll include some links in the description that you can check out if you want to see some videos on this.
So first of all, this is not water. It's a fluorochemical developed by 3M. They named it the Novac. So it's non-electrically conductive, non-corrosive, non-toxic, and environmental friendly. This is the same liquid as in the container. Take it out, drip it out a bit.
This is the type of thing you might see in data processing centers, but it's not something that you'd actually see for home users. If you're interested in seeing more of this video, I'll include a link to it in the description. These are also used just widely as a solvent for cleaning purposes, although their structure is a little bit concerning based on some of my research that we've actually published. And so the case that's mentioned by Red Nigel is that it can be used in fire suppression systems. Now, the one that he used isn't routinely used for fire suppression. The one that's actually used for fire suppression is the same one that's used for data cooling centers, although in principle it could be. And so what are these Novex solvents? I suggested to you that they're fluorinated, but they're not inert. So let's just talk about the fluorinated portion to start. So this is the structure of Novex 649. This is made by a company called 3M. All of the Novex are produced by 3M. And this has an interesting ketone group. I look at this and I think immediately toxic because this resembles hexafluoroacetone, which is toxic. Does that mean this is toxic? Maybe, maybe not. I haven't done toxicological studies. I'd be interested to know what other people have to say, though. Now, amongst the other Novex solvents, they actually tend to have a different structure for the most part. And so this includes Novex 7000 and 7100. Novex 7100 was the one that was shown in the Red Nigel video. Although there are other Novex solvents which are still hydrofluoroethers. So we have this fluorinated group as well as this hydrocarbon group, and we have an ether. And so this is called a hydrofluoroether. Now, they make other hydrofluoroethers which have ethyl groups instead of methyl groups. They also have a couple products which are derived from Novex 649. As you can see here, there's a couple of those. And there's also Novex 7700, which I actually struggled to find the structure for. Looking at its structure, it's definitely a little bit concerning because that is super duper fluorinated. So if you're not familiar with perfluorinated compounds, these can often be persistent organic pollutants, and they're so persistent that they fall into their own category called PFAS, perfluoroalkyl substances. Now, while it's claimed that these are preferable to pre-existing refrigerants and other perfluoro compounds that had chlorine as well, because these were ozone depleting, these do not have any chlorine or halogens which could possibly be ozone depleting, but they do still have a global warming potential. So the main ones we're going to be talking about in this video are HFE 7000 and 7100, as well as other things that resemble this structure. So as I just mentioned, the Novex solvents are non-ozone depleting, and they still do have some global warming potential, although this is lower than some of the other stuff that's been made before. The difference here is these have a shorter lifetime in the atmosphere. I wasn't able to find any papers discussing the decomposition of these compounds. If you're able to find any of these papers, or if you have any on hand, please comment them and I'll pin the most relevant comment. And so this begs the question, 3M, where does all the Novex go? And I think Tom from Explosions and Fire gives us a pretty good answer. The atmosphere is nature's bin. It just goes up there. What happens after it goes in the bin isn't our issue. Am I claiming that that's what 3M's saying? No. But I'd like to know what they are saying. So 3M, if you're out there and you're listening, I'd love to know if you have any data on the decomposition of these compounds. And if it isn't in the published literature, I'd really encourage you to publish a paper so that you could just put all of our minds at ease. Another similar class of molecules to the HFEs produced by Novex is the Fluorains. So Fluorains are a group of anesthetics. They're used in veterinary and human medicine. Although some of them are preferred for specific applications, there's one amongst these called Methoxyflurane. And you can see that Methoxyflurane has a CF2OCH3 group. And so methoxyflurane is an interesting example of a hydrofluoroether, which has the same structure as the Novex, but is routinely used in some countries. There's some difference between these fluorains here. Some of them have an OCF2H, some of them have an OCH2F, and methoxyflurane has an OCH3. Does this mean that they have different metabolites? Yes, and we're going to talk about that in a bit. And so I haven't mentioned it yet, but this video is made in honor of the channel hitting 50,000 subscribers. I'd like to thank you all for your support. If you're not subscribed yet and you're watching most of the videos, I'd encourage you to subscribe, but it's totally your choice. If you don't want to, you don't have to. So this is a subscriber special, Joey. Why are you talking about this? Well, it turns out that I've worked in labs with these solvents. So I've worked in a lab with Novex 7100 and 7000, and we've used these as solvents for polymers for various different purposes, as I worked in a lab that produced fluoropolymers, and it's difficult to find solvents that dissolve these. And so it was observed long before I joined the lab that when you mix Novex 7100 in certain reactions as a solvent, it tended to produce some sort of white precipitate. And so this was confusing. This is where Benson enters the picture. Benson was the grad student that first trained me to be an organic chemist. Benson's awesome. Here's a couple pictures of Benson. And there's one other cool guy there. There's Umamoto reagent Umamoto. This picture's from a conference I also attended in Oxford, which was a really fun experience. Okay, so back to Novex 7100. So Benson was tasked with working on this project, figuring out what the white precipitate was, why it was forming. And so one of the things he observed was that when it reacts with triethylamine, it produces this white precipitate. And so he's tracked it down from sometimes in some reactions this happens to, okay, we have a white precipitate. Let's see if we can isolate it and figure out what it is. And so as a key part of his PhD work, Benson discovered that when you mix hydrofluoroethers with some tertiary amines, you end up getting these white solids. And these white solids are quaternary ammonium perfluoroalkoxide salts. And so these are the types of products you get. Because Novex 7100 is a mixture of two different chemicals, you end up getting a mixture of salts as your product. So if you choose a hydrofluoroether, which is just one single compound, you'll only get one single product. And so you might be thinking, how is this related to what we talked about earlier? Well, these are inert solvents. These are fluorinated solvents. These don't seem so inert all of a sudden because triethylamine is a routine reagent. That's a very common reagent. So these so-called inert solvents aren't inert. What happens? Once you form these white solids, these perfluoroalkoxides, they can decompose into an acyl fluoride, which might be really toxic. You can tell that these are PFAS compounds. The products of these reactions are going to be perfluoroalkyl substances that aren't going to be breaking down anytime soon, as well as fluoride. And depending on how the fluoride's generated, you might be generating HF, which is not great. And so what is this reaction and why does it happen? Well, a hydrofluoroether is a little bit like dimethyl sulfate or methyl triflate. These are methylating agents that are quite toxic. Now, am I saying that hydrofluoroethers are as toxic as dimethyl sulfate? No, by no means. But they shouldn't necessarily be considered non-toxic, as we can see it routinely methylates a tertiary amine. So this could potentially have methylating effects in the body. Does this mean it's methylating solely tertiary amines? Not necessarily. It could be methylating other nucleophiles. And so the overall reaction shown here is that first the nucleophile is methylated. This generates HF as well as that acyl fluoride we were just talking about. Now that acyl fluoride that we just formed, however, that's a far better electrophile. And so that can react with almost anything. That's a very electrophilic electrophile. That can react with nucleophiles that are even poor nucleophiles. And guess what happens? It forms even more HF. Where do I come into all this? So Benson had shown that this works with Novex 7100, 7000, and he'd also shown that it works with the 1-carbon and 2-carbon hydrofluoroethers. Although before his PhD, he wasn't able to finish this before he defended his thesis. And so this is where I come in. So I had already been doing some method chemistry. I decided that I was going to find a good method for converting these compounds into their corresponding salts. Maybe they'd have a synthetic utility. And so in this work, I developed a method which was an improvement from the existing method, and we still had one problem, which was it was seemingly random which tertiary amines would react and which ones wouldn't. And so this is when Benson suggested that I looked at something called Mayer's N parameters, Mayer's nucleophilicity parameters. These parameters are derived from SN1 reactivity, although this is an SN2 reaction. We found good trends between the reactivity of tertiary amines and the corresponding yields of perfluoroalkoxide salts. So I'll just briefly show a plot here showing that the larger the nucleophilicity parameter, the higher the yield of the salt, or the more likely it is that the salt was formed. The takeaway from this is that the nucleophilicity of the nucleophile matters in terms of how much demethylation is going to occur. And as I stated earlier, triethylamine worked in the case of Novex 7100 and 7000, but it didn't work in my case, which suggests that Novex 7000 and 7100 are slightly better alkylating agents than the shorter chain hydrofluoroethers that I examined. And so there are definitely nucleophiles in the body with a nucleophilicity comparable to that shown here. And even if the nucleophiles are weaker, some nucleophiles in the body will still get alkylated. It's just a slower process. Nucleophilicity parameters are kinetically derived parameters, and it's a logarithmic scale. So as this decreases, it's decreasing by orders of magnitude. Again, as stated earlier, the methylation is a little bit more challenging, but once the methylation occurs, you form that acyl fluoride, which is really reactive, and that could react with other stuff. So I just want to take a minute and show you some of the setups from this chemistry because the setups are somewhat unique. Here we can see an ACE glass reactor with a pressure gauge so that we could pressurize the vessel and make sure it wasn't overpressurized past atmospheric pressure, or if it was within acceptable tolerances. So the way that we would charge these vessels was on a gas line, and this is because some of the hydrofluoroethers, especially the low molecular weight ones, tend to be gases. Also, sometimes the amines we were using, like trimethylamine, were gases, so we had to do that with a gas line. And here's a picture of one of the perfluoroalkoxide salts that I made. So the cool thing about these salts is they're relatively stable under inert conditions, but they're not stable under atmospheric conditions. So if you have these salts in air in the presence of water, they will just decompose to form acyl fluorides and HF. So not great. So back to the anesthetics, methoxyflurane. Methoxyflurane was used as an anesthetic in the US, but it was withdrawn from the market by the FDA in 2005. The main reason it was withdrawn was it was known to cause nephrotoxicity, which is toxicity towards the kidneys. It also causes toxicity in some other areas, but the main concern was nephrotoxicity. And so one biomarker that they looked at was elevated fluoride levels. Most of the time, people had 1 micromolar or lower fluoride levels in their serum, in their blood. Although post-op, for about 3 days after, they had serum fluoride levels around 140 micromolar, which is definitely concerning to say the least. The authors of this research paper believe that the toxicity of the kidneys comes from the presence of fluoride and or from other metabolites, but they don't mention this acylation problem that I discussed earlier. And so they compared this to the other anesthetics, and here's what they have to say. Isoflurane and N-fluorane are more resistant to biodegradation and less soluble. They were examined in detail and almost without exception, peak fluoride levels were less than 50 micromolar and were short-lived. Laboratory or clinical abnormalities of renal function were not observed. So they said they didn't see any issues with the kidneys when these other anesthetics were used, only when methoxyflurane was used. So there was lots of cases of nephrotoxicity from methoxyflurane, and there was even at least 10 deaths associated with it. And so another thing that they had to say was, sevoflurane is relatively insoluble in tissues, but is more readily biodegraded than isoflurane. These findings support the concept that both the extent to which fluoride levels increase and the duration that they remained increased were major factors in the development of methoxyflurane nephrotoxicity. And this is the point that I want to highlight here. However, this issue is still not completely resolved because it is possible that other metabolites unique to methoxyflurane, such as dichloroacetic acid, which is very toxic by the way, together with fluoride, might be the cause of methoxyflurane nephrotoxicity. So these researchers are claiming maybe it isn't just from the fluoride, maybe it's other metabolites, but I would still lean towards that acyl fluoride that's being produced definitely being one of the culprits. The other trend that I want to point out here is that the N-fluorane and the isoflurane have 2 fluorines on that methyl group. They don't degrade that much. The sevoflurane has 1 fluorine on that group. It degrades a little bit, but not as much as methoxyflurane. But the methoxyflurane has just a CH3, and that degrades the most. And so what I believe is happening is that as you get more and more fluorines on that methyl group, it becomes harder for a nucleophile to attack it and demethylate it, causing metabolism to corresponding byproducts. Now, it could also be that some of the metabolic byproducts for these aren't as toxic, but sevoflurane is going to be producing hexafluoroisopropanol, and that's not great either. And if it's not producing that, it's producing hexafluoroacetone, which is also not great. Now, there was one quote in this paper which I really liked, and I think this should be inspirational for all of the researchers out there who are actively doing science, who sometimes feel like they can't make a difference. Amazingly, no lawsuits were filed citing methoxyflurane nephrotoxicity as a cause of injury. Rather, compelling scientific evidence led practitioners and the manufacturer to abandon methoxyflurane. All involved in these studies derived a great sense of satisfaction knowing that our research helped to shape clinical practice in a way that resulted in a decrease in anesthetic-related morbidity and mortality. They did research, they found it was bad, and the manufacturers pulled it. No lawsuits involved. That's pretty awesome. I think we should be striving for that as much as possible. This paper was published in 2006. This is what another paper has to say about this. Subsequent research suggested that there are additional risks potentially relevant to recurrent patient or occupational exposure, specifically greater than expected fluoride production after repeated low-dose exposure, increased fluoride production due to medicated-caused hepatic enzyme induction, fluoride deposition in bone potentially acting as a slow-release fluoride compartment, which suggests a risk of skeletal fluorosis and hepatotoxicity. Now, one of the things that they claimed in that 2006 paper is that if they kept the fluoride levels in the blood below 50 micromolar, it tended to have less nephrotoxicity. And so this justified people to only use it as an acute pain treatment as an alternative to a full-on sedative. And so it's still not used in the US, although it is used in New Zealand, Australia, Ireland, the United Kingdom, and Canada. And it was only reintroduced to Canada a few years ago, which is actually quite upsetting given that this paper in 2006 was published at least 12 years before it was reapproved in Canada, which is completely unacceptable in my mind. And so they're giving it as an acute pain treatment. It is for a different indication, and it is at a lower dose, but that doesn't mean that it's still not toxic. As we saw in that original paper, they said, we're still not entirely sure about the toxicity. And if you're making decisions based on the serum fluoride levels, that's a cause for concern because we don't know if that's the actual cause yet. And I think people need to look into whether or not the acylation of biological residues has a part to play in this. Another concerning factor is a lot of the time these Penthrox inhalers, which is the brand name for this, are self-administered. So people, including kids, are able to self-administer these things, which if dosed at too high of a level, can be nephrotoxic. That's pretty concerning. I think that's pretty concerning. So to summarize what I believe is happening here, subsequent research needs to confirm whether or not this is occurring, is that first, methoxyflurane is able to enter the body. That is then able to form dichloroacetyl fluoride, dichloroacetic acid, methyl dichloroacetate, which is known in the literature, HF, as well as methylated residues in the body, potentially the kidney, which is where we see the toxicity, as well as dichloroacetylation of biological residues. In my mind, this is extremely concerning, and I think subsequent research needs to be done to look into this. I don't know if there's a good justification for why this is used over other potential pain-mediating anesthetics, but I believe the nephrotoxicity alone is a good enough reason to stop its use. And so this whole time I've been talking about the Novex solvents and methylation of tertiary amines. So you might be wondering, Joey, how do you know that methoxyflurane also methylates tertiary amines? Well, we actually showed this. And so in one of our papers, we demonstrated that methoxyflurane is able to methylate trimethylamine, as well as DABCO, which is another tertiary amine base. Was this chemistry super clean? No, because other chemistry can happen with the methoxyflurane as well that causes it to be a little bit messier. But the point is that it does methylate stuff the same way that the Novex do. So this is a cause for concern, and definitely further experimentation and research is needed to understand this process. And so back to the point about Novex. There's no reason that the same thing couldn't be happening in the Novex. You can still do the methylation, and you can still form an acyl fluoride, which can react with biological residues. Now, in the case of methoxyflurane, at least those break down, right? You get dichloroacetic acid, that will break down eventually. But the perfluorinated analogs are way harder to break down, and those are just going to be more PFAS in the environment, just like perfluorooctanoic acid, which has been haunting us for years. I think that more research is needed in terms of the environmental breakdown products of the Novex solvents, especially the hydrofluoroethers, such as Novex 7000 and 7100. But also, I think we need to look at what happens biologically to people who are exposed to these solvents, because you see people such as Nile Red handling this with their bare fingers.
But I think that all this water might have actually been worse than the fire.
Is that going to be causing issues? I would be concerned about it. I wouldn't handle it with bare hands. And I come from a lab that's worked with this stuff routinely for years. So I think we need to take a better look at the toxicity of these Novex solvents. I think we also need to take a look at what happens when methoxyflurane is in the presence of biological residues. Does it irreversibly alkylate or acylate these residues? I think that's something that should be examined. And I think the best case of this would be looking at if this is the actual cause of the nephrotoxicity for methoxyflurane. Here you can see kind of what I'm suggesting could happen below. You have some nucleophile in your kidney, it reacts with methoxyflurane or an HFE such as Novec. This then methylates or it acylates it, and that would be irreversible, probably causing toxicity. So if you have any experience in this area and you have anything to add, I'd encourage you to leave a comment down below. I hope you've enjoyed this video, and I hope you have a great day.